So following on from our last video where I gave an introductory sort of spiel on the importance of setting up your relative fuel pressure multiplier table and what end effects it has on the required fuel duty that gets implemented inside the engine, I wanted to follow that up with, instead of a simulated version showing you how the table works and its effect, looking at an actual bit of information off a car where it was essentially turning off the closed loop lambda due to the actions that we spoke about in the last video. But to repeat it here, whenever you have anything that interrupts how the engine works in terms of its spark scheduling or its fuel component that gets put into the engine, you essentially can't rely on the lambda reading. This varies between different setups on different cars and the sort of hardware that you run, what type of manufacturer of lambda sensor it is. Some are better than others, but for all intensive purposes, disregarding which type you have, it's good practice to not rely on the closed loop lambda in that situation. So it's critically important to set up this table, and we did also mention you do have real world situations, be they through poor design. It could simply be a fact of a component failing. It could be something simple as a blocked fuel filter, you don't know, but you need to be able to counter all of these situations. So that's where the relative fuel pressure table really comes in. So over on the right hand side here, we've got just a basic worksheet, and it lets you have a look at the two important variables that we were mentioning. So one of them was relative fuel pressure, which is the grey trace you see here, and the other one is the implementation of it, which are the actual numbers inside the table here. So the relative fuel pressure multiplier based on the relative fuel pressure. And what you'll see up in the top table here is we have a status of the closed loop lambda control, and you'll see that it's enabled up here on bank 1 up until this point where it becomes disabled. And if you look down in the bottom graph here, the reason it's disabled is we have a torque ignition severity being applied. Some of you may want to know what that is. So what it is a traction control request coming out of the ECU. I'll turn that off now so it doesn't interfere too much with what I want to show you. But suffice it to say, whenever you have something like this, your closed loop lambda state is disabled. Now the perfect storm is it's all fine and good if your fuel pressure is stable, but in this case we had a situation where the fuel pressure dropped massively. You can see here down to 2 bar relative fuel pressure, whereas the normal is 3200. So if you have a look closely at this graph, 3200 is our normal base of a 1. Which is roughly what we're getting here as well. It's a little bit lower because the fuel pressure is drifting slightly higher, which corresponds to what's set up in this table. Now, what's the difference, I hear you all asking? So the difference is we have a closed loop lambda target of 0.7. It's tracking reasonably well to that. If you have a look at the lambda error, which disregards using the fuel multi-CLL, you can see it's pretty much exactly where it needs to be. Now you imagine if you had all ones populated in this table and you had a massive fuel pressure drop like what we see here, the closed loop lambda's off, so the ECU isn't doing any correction, and this final lambda that you're measuring in the exhaust would theoretically be a lot less rich than what you're commanding it to be. And depending on your engine type, they sort of don't like that, especially when you're up around 33 pounds per square inch of boost pressure in gauge terms, 3300 millibar or thereabouts. So as soon as our fuel pressure drops down, we see our relative fuel pressure multiplier, which comes from this table, being actioned. And the end result is our lambda, instead of spiking potentially leaner than what we want it to be, is actually going the other way, and it's richer. So you end up saving your engine essentially. And hopefully that explains to you in a practical example, real world example, why setting up this table is so important and why I recommend everybody do it. Hopefully that's been of use to you. If you want me to put up something else about that subject, then just let me know, or otherwise we'll move on to another topic in the next video.